So raster data, just like any other GIS data, is stored with a coordinate system that allows that spatial data to be put in its proper location. So raster data, or DEMs like this one, can have a geographic coordinate system, and sometimes these tend to straighten things out so they kind of have this odd shape associated with them, where because of the and this would be very different than this conic coordinate system that's shown here. So how do we deal with all this? Well, when we're downloading that data, we're going to want to project it into the coordinate system that we're using. So in this example here, the output coordinate system is a UTM zone 10 north. And when we do this, some things that we want to keep in mind are that we need to know the coordinate system we're projecting into. We may need to know the datum that we're projecting into, and we have to define the resampling technique, which once again, I would recommend not nearest neighbor, but bicubic convolution for the resampling technique, because otherwise you're more likely to get artifact. Besides projecting raster, we may also need to georeference certain rasters. An example of this would be if you scanned in an old map and you wanted to put it in its proper geographic location into the GIS. And in order to do that, you would do a transformation, and these calculate the real world coordinates, and they're based on points that you know both on the scanned image and in the real world. So for example, you might know exactly where this point is, and this point, and this point, and that point, and that point. And you take all of those together, and you do a sort of transformation on it where it's warped in space to put it in its proper geographic coordinates. And when you do this transformation, there's basically two different types of transformations that you can do. You can do an affine transformation where things are where things are transformed in an affine sort of manner, which means they can be scaled up and down, they can be rotated, but lines that were parallel before the transformation are also parallel after the transformation, as we can see in these edges here. And there's another type of transformation which is based on polynomials instead of an affine transformation. Here we see the second order polynomial or third order polynomial, in which case a transformation still takes place, but but parallel lines are no longer parallel. It's not an affine transformation, so that we kind of have this sort of stranger shapes here resulting, and sometimes this is called rubber sheeting. After we do any sorts of these transformations, we can look at the RMS error, which means the root mean squared error. And this is going to tell us how close those control points are that we started with, how close those are after the transformation to where we expected them to be. And this RMS error, or RMSE, is an overall assessment of how accurate the map is to where it can be with respect to those real-world coordinates.